far beyond the familiar order of the planets, far beyond the last stable echoes of Neptune's gravity, the solar system begins to behave strangely. At distances so extreme that sunlight becomes a historical memory rather than an illumination, the paths of distant objects refuse to line up with what gravity alone should produce. Their orbits are tilted, stretched, clustered, as if something massive is quietly rearranging the architecture from the shadows. This is not a story about discovery yet. This is a story about absence, about the discomfort of realizing that the map we trust may still be incomplete. In an era when we can image planets around distant stars and reconstruct the first galaxies from cosmic background radiation, the idea that our own solar system may still be hiding something enormous feels almost unsettling. At deep space inquiry, we find that unease more revealing than any easy answer. To understand why Planet 9 is even considered plausible, we need to unlearn the idea that the solar system simply fades away after Neptune. The region beyond it is not a void but a sparsely populated frontier filled with icy remnants known as trans-Neptunian objects. These bodies are relics from the early solar system, frozen records of how planets formed and migrated. The first of them, Pluto, was discovered in 1930 and stood alone for decades, giving the false impression that it was an anomaly. It was not. When surveys finally became sensitive enough, thousands of additional objects emerged, many following orbits that defied neat categorization. Among them was Sedna, whose elongated and detached orbit suggested that something powerful had once reached into the outer solar system and left a lasting imprint. One strange orbit can be dismissed as coincidence. A population of them cannot. As more distant objects were cataloged, astronomers noticed a pattern that was statistically difficult to ignore. Their orbits appeared clustered in orientation and aligned in space, far more than random chance would allow. This behavior hinted at long-term gravitational sculpting, not a single event but a persistent influence acting over billions of years. Models incorporating a distant, massive perturber began to reproduce these orbital configurations with surprising consistency. When researchers like Mike Brown applied rigorous statistical analysis, the odds of the observed clustering occurring by chance dropped to vanishingly small values. The implication was uncomfortable. If the math was right, then something large was missing from our inventory of the solar system. If a planet several times the mass of Earth exists in our own system, why haven't we simply photographed it? The answer lies in how light behaves at extreme distances. The brightness of a distant planet falls off not just with distance from Earth, but with distance from the Sun squared twice over, once on the way out and once on the way back. By the time sunlight reaches hundreds of astronomical units and reflects back, it is unimaginably faint. Even wide-field optical surveys that have revolutionized astronomy struggle under these conditions. This is why Planet 9, if it exists, is not a failure of observation, but a reminder of physical limits. It forces us to acknowledge that there are regimes of space where detection becomes an exercise in patience rather than capability. Where visible light fails, infrared offers another approach. All planets emit heat, however faint, and that emission persists even when reflected sunlight does not. By comparing data from decades-old infrared sky surveys, researchers identified a clever workaround. If Planet 9 moves slowly across the sky, its position should shift measurably over decades while distant galaxies remain fixed. By cross-referencing archival data separated by more than 20 years, astronomers narrowed millions of infrared sources down to a handful of candidates. One in particular displayed motion consistent with predictions. At Deep Space Inquiry, we view this not as proof, but as something more interesting. It is the first time absence has begun to leave a measurable trace. Speculation ends when observation begins, and that moment is approaching. The Vera Rubin Observatory represents a fundamental shift in how we survey the sky. With its unprecedented sensitivity and cadence, it will repeatedly image the entire visible sky for a decade, tracking faint moving objects with precision no previous telescope could match. If Planet 9 exists within the predicted range, Rubin will not miss it, and if it does not exist, that absence will be equally informative. Science advances not by defending ideas, but by testing them until only the most resilient remain. The most honest scientific question is not whether Planet 9 exists, but what it means if it does not. Several alternative explanations remain viable. One possibility is that the clustering of orbits emerges from the collective gravity of many smaller bodies acting together rather than one dominant planet. Another is that the early solar system experienced a close stellar encounter, a gravitational brush with another star that permanently reshaped its outskirts. More exotic ideas even suggest the capture of a primordial black hole, an object with planetary mass but stellar density, invisible except through its gravity. There are also theories that propose subtle modifications to gravity itself, such as modified Newtonian dynamics, though these remain controversial. What matters is not which explanation wins, but that each forces us to confront how little we truly know about the solar system's deep past. At Deep Space Inquiry, we are less interested in restoring a ninth planet for nostalgia's sake than in understanding why the universe resists closure. The outer solar system is not just a place, but a boundary between certainty and ignorance. Whether Planet 9 is a planet, a collective effect, or nothing at all, the search itself reveals something essential about science. We keep looking not because answers are guaranteed, but because questions reshape how we see ourselves in the cosmos. As new data arrives and old assumptions fall away, one truth remains. The universe does not owe us completeness, only the chance to keep asking,